Yes. Good morning all. We are welcoming for the third day of offline FDP program. Myself Dr. M. Pushpavalli, and today I am going to discuss about the converter, KY boost converter. KY boost converter. In the KY boost converter, I have taken one paper, and in that how the flow is there, the same way we try to solve. And our faculty main aim is to convert everything into publication. So today I am going to discuss in that aspect view how one possible decision we have taken for one paper, and how to develop from that paper to another level and to move on to the publication. While I am starting my KY boost converter, this is one first paper I have started, and from that I have done modification and so many modification, and after to my publication nearly 8 papers I have written only from this KY boost converter and only from this paper. So as I think there are so many converters are there. Why the KY boost converter? I think yesterday also sir have given some introduction about the KY boost converter. Why the KY boost? The author itself, the name of the author of KIHWYTYAU. So they developed that KY, from the name itself they have taken. We have seen Buck boost, Bug boost, Sepic, so many converters are there. Still, why this KY boost converter become popular now? Because there are so many reasons are there, but the specific reason is the system is stable one. KY boost converter is a stable converter. How they justified it is a stable converter now? Finding out the transfer function, and from this transfer function they plot the poles and zeros, and all the poles and zeros lie on the left half of the S-plane, and they ensure that this is a stable converter. We may use it for any purposes. So actually this author also have put so many papers related to KY boost converter, but what is bring that now? By doing some modifications in the paper only they have developed. So first, what is our flow today? First we will do KY boost converter, normally this converter, and in the KY boost converter we try to get the transfer function. Actually we want to write the transfer function. Normally the state space equation will be more useful. State space equation we will write. State space equation depends upon the energy storage element. Depending on the current flowing through the inductor and the voltage across the capacitor, we will take it and we will solve it and we will find out. But that is somewhat been that, but we will try to write the transfer function, and then we will apply the PI controller and all. So using PI controller, we may see to that how it is been reducing the error and all, and we will use how to use the FLC controller. So this is the extended version. It's not only stopped here. If I want to do it in furthermore, I can go for multi-input KY boost converter. So what is multi-input KY boost converter? 2 input. The same way here only one single input is there, we can able to develop. Multi-input na 2 level of input. Why we are giving 2 level of input na? Again the multi-input may be step into that we have a solar and wind. So we may use one input for solar and another input for wind. So we have 2 inputs, solar and wind, and obviously we are using solar and wind in a KY boost converter. So in that our output of the KY boost converter will be given to the inverter, and from the inverter we given to the load. And in that aspect when you use, we may say to that there is a power factor improvement is there, and THD, total harmonic destruction, will be reduced, and we can go for another way, we can go with energy management also. So energy management with battery arrangement. So when you see to that a small KY boost converter, in this paper they have just been completed over here. When I go through this paper, you may see to that KY boost converter is being proposed. KY boost converter is proposed, the modes of operation have been developed, they have written the equation, and from the equation they have obtained the small signal AC model, and from that only they derived this transfer function. But now we will see how we can derive the transfer function for any converter using the steps, and then they have been obtained the voltage gain, that is M equal to V0 by V in. They have taken the voltage gain versus duty cycle. So this this is the way we can see what will be the voltage by varying the duty cycle. And the next method is they have been calculated the current versus efficiency. By increasing the load current, they calculated the efficiency, output power by input power, and there they have taken all the losses into the account. So this is, they have developed the paper, and I told that this one concept have been only with the KY boost converter we are developing. KY boost converter to how to obtain the transfer function, and we are using the PI controller in the feedback, and we are doing the FLC controller. But I am saying that in another level, when I move on to that, we can go with the multi-input. Multi-input, we may take solar as well as wind in the way, and solar and wind, we are using energy management with the help of battery. So not only this, we may compare this multi-input with the various level of converters also. Various level multi-input buck converter, boost converter, buck boost converter, then Lu converter, Sepik converter, buck boost, Lu, Sepik. All this converter we can analyze. How we can analyze? We can again analyze in open loop as well as in the closed loop. So open loop, while we are analyzing, we have to ensure that open loop have contains of a losses have been, we are saying that losses has to be reduced. So switching losses should be reduced. When I go and analyze with the closed loop condition, in the closed loop condition, we may take the Bode plot, we may plot pole zeros configuration, we can plot the pole zero for the stability, and it should be lie on this left off of the S-plane, and going with the closed loop, we can take all the time, rise time, fall time, settling time, then a steady state error. So one thing, we can move all this, one converter when you take it into the account, we may convert that converter in another level of thinking that this will proceed you in this way. So here we are going to see this one and how it is working under the multi-input. Multi-input, the afternoon session I will take it, and morning session I try to take this Sky Boost converter, transfer function, PI, and along with how to develop the FLC. So first, we may develop the KY boost converter in the MATLAB first. First step we will discuss to see the KY boost converter. So I think I have taken the value. You may develop the KY boost converter, and we have seen the modes of operation is there. So I think Sarah have explained yesterday the modes of operation while we are working. So same KY boost converter we have been taking, just give this connection. First we will give this connection, and we will see how to get the transfer function for this circuit. So while we are taking the input, the C1 value is 1000 microfarad. I will write all the values. So you try to develop this KY boost converter, and along with the input inductance 15 microhenry and 470 microfarad. Okay, and actually here in this paper they have given the switching frequency, the same switching frequency only we have taken into the account. While we have been analyzing, the switching frequency value is 195 kilohertz. That is only we are going to take. Li is 15 microhenry, and the input is 12 volt, and while substituting our V0 by Vin, that value is 1 minus D by 2 divided by 2 minus D. This is our duty cycle value. So here while we put D equal to 0.5, and we will get, so by giving 12 volt we will get around 36 volt. So thing 12 volt and we are getting 36 volt and the rated output current is 2.5. Switching frequency is 195. Input inductance value is given 15 microhenry and L naught is also same value only, and the CM capacitance, that is 1000 microfarad, and output capacitance is around 470 microfarad. So once you develop this KY boost converter, you may see to that you may get the waveform. Actually, I have done a small change in the waveform. If you want to change the style of the waveform in the scope, here itself you can change it. Okay, you try to connect the component. So any converter you want to analyze, you just choose one base paper and do the simulation of that base paper, and from that simulation we may take into the another level of analyzing the circuit. So this paper one stage is only there. So I have connected the same component, replica. I have done the multi-input converter, and that multi-input converter works properly. Then I go and connected with the solar and wind. One is because we have to check under the non-linear load condition also, because while we are connecting directly the supply, PV and wind is not a linear source, it's a non-linear source. So it need a disturbance. So definitely, so we have to apply one disturbance and we have to check that condition. Taken components. And the pulse, how I given the pulse now, when you see to that 195 kilohertz. So 195 kilohertz na we can put it 1 divided by 195 kilohertz. Okay, and you give it as a pulse. Amplitude is, period is 195 kilohertz in the pulse. So period we can give 1 by 195 kilohertz, and pulse width is around 50%. Pulse width is 50%, and for the first switch I didn't give any phase delay. But when you give for the second switch, I give some 20% as a phase delay. So when I move 1 divided by, okay, 1 divided by 195, 1 kilohertz. Okay. And here I have taken that phase delay as a 1 e power minus 4. How the calculation of first switch I didn't give any phase delay, while I gave some 20% of phase delay. So 1 by 195 into e power 3, it is nothing but 1 e power minus 4. So this is the phase delay I gave for the second switch. Okay. So after have you simulated? See, after simulating you will get it. I gave 25 volt as my input and around 85 volt I gave as a output depending on the duty cycle. And when you go and you want to vary here, you have a style in that you may choose the color, axis color and all. And here also you can change it. We need not to do it in our dock. when I dock, and we will do it everything in command window. But here itself I can change the settings, everything here itself. So it will be easy for you. And this thickness, if I choose it like that way, the thickness I can change the color. So my MATLAB scope parameter itself I can change it. Okay, and when you go through this, I have to find out the transfer function. So to find out the transfer function, I just search for ID data. ID data, we have two things, ID data source, ID data sink. So connect ID data sink here itself. Okay, you just paste the ID data sink here. You connect the input, this is my input, and connect the output. After the voltage measurement, you have both the input and output block. You connect it over here. Okay, after connecting over here, you may use the command. Actually, you have a file here. You may give it any file. I am giving my data file name as a data itself. So give data. Okay, and here while you done this, you may give it plot data. If I give plot data, sorry, I have to run. Once you give, I have to run the program. Once you done it and you give plot data in the command window, then you can see to that your input and output you will obtain here. And actually input variable name as a U1 and output variable name as a Y1. So this is the data, the name will be stored in the command window. After plotting this, you have to get the variable in the name of Y. So you give Y is for output, Y data equal to Y. So you will get Y plot. Okay, the array, the variable, it will be stored in the variable name of Y, and then you do it for X. You do it for X, or you may keep it as a name as a U. In control system, how we will mention. So here, sorry, I put it as a U dot data dot U dot data dot data dot U. So you get our input as well as we get our output. So now we are going to use, next we are going to use, we have to obtain the transfer function. So to obtain the transfer function, use this command. To obtain the transfer function, ID data, and this is my sampling time, I have kept as a 1, and actually the sampling time you may go through here, and here the time is 0.1. You have to choose it as a 0.1. Output comma, input comma, and the sampling time, that is the syntax for this. Okay, so you may get it that Y1 and U1. So after putting that, then you have to get the transfer function. So to get the transfer function, actually normally the transfer function we used to give any variable name you can give, H. And this is number of energy storage element. So in this circuit, when I go with, I have 2 inductance and 2 capacitance. So I have to give the value as a 4. So, okay. Actually we have to first get HVSys. You just connect first, connect this and try to get the variable in the command window. Okay, after that you have to use, actually we have to get the system variable. The same way we have to use hvsys equal to id data the same value formula. I have to take it. Okay, then I have to use this h equal to tfest. I am using y4 now, it's the number of energy storage element. After getting this, I'll get my transfer function. After getting my transfer function, I may use the Bode plot to plot this transfer function. I get my Bode plot, and after getting the Bode plot, I have to use the pole zero map as well as gain margin and phase margin value. So I have, this is the formula to calculate the gain margin and phase margin. After finding gain margin and phase margin, we have to get the pole zero map. So this is the pole zero map. So from one single converter, we may obtain, using all these commands, we can plot the Bode plot, we can find out the transfer function, and we can obtain the pole zero plot also. So I think when you go with this command, all this are lying on the left half of the S-plane. So we can state to that it is a stable system. So these are the commands, we have to use it while I have to obtain the value. So plot, we can, that is not necessary, but once we use this ID data in our variable, we may plot it. So use the following commands to obtain the variables. Use plot data, and then while I have to obtain my y value, y equal to data dot y and u equal to data dot u. Y is for my output and u is for my input. After getting that, data equal to id data y comma u comma 0.1. It's a sampling time, we have given that in id data block. After finding this id data, then we have to use this hvsys. We have to upload that system variable hvsys equal to data comma y comma u comma 0.1, and then we have to get the transfer function h equal to tfest hvsys comma for number of energy storage element, and then we have to, then we can put Bode of h, we get the Bode plot, then gain margin, phase margin, that is margin of h, we can get our gain margin, phase margin, gain crossover frequency, phase crossover frequency and all. Then we have to use PZ map, pole zero map, for poles and zeros. You want the values of poles and zeros, you may use the plot to okay, whatever we are giving, that you will get it. Pole zero map. After finding pole zero map, you need a value of pole zero map. You have to use the command P comma Z PZ map of H. It will give the poles and zeros values also. So actually one converter, we may get our transfer function, we may get our Bode plot, and we get all these things, and ensure we can say to that, along with that we can find the stability of the system. So it's a basic KY boost converter. This they have done. Till when you take that paper, they have done all these things, transfer function they obtained, and they ensured pole zero. After that they have done two things while we look up on the when you go to this you may see to that the voltage gain value is there. They varied the duty cycles from 0.5 to 0.95 they varied, because their duty cycle they get 50%. When I vary my duty cycle, my corresponding voltage gain is also increasing. By that they have drawn this graph. This is one graph they plotted, and another graph is they find out the efficiency, output by input. So they incorporate the switching losses, diode losses and all, and the losses at the inductance using these formulas. And P out they calculated V naught into I naught, and through the output only including all this conduction losses, switching losses and all they plotted. So while see to that my current, when is my current they vary till 2.5 ampere. So till 2.5 ampere my efficiency is almost maintained till 85% to 75%. So these are all back end work. You may increase your duty cycle and see to that how it has been varying. So when I go and taken my KY boost converter, if I am giving my pulse width is about some 60% or 70% off on, okay, and here if I give again at that value, my voltage gain also correspondingly increases. See, previously it is around 85 volt, now it is increases to 150 volt. So one converter if you take it, and from the one converter you vary the duty cycle, and by varying the duty cycle and then calculate the losses, and you may obtain. So this is the one KY boost converter they have taken into the account and they have solved. Okay. Sir?